Okay. So, last time we defined the radius and interval of convergence, and near the end we didn't quite get to it in the lecture, but it's in the lecture notes, so I'm going to just kind of assume that we've all read it, or we will read it. That inside the radius of convergence, power series are differentiable, and you can get its derivatives just by doing term-by-term differentiation. Okay, this falls out, as the lecture notes show, this falls out of a theorem we proved last semester, that if you have uniform convergence, and a couple other hypotheses, then the derivatives of the sequence converge to the derivative of the function they're converging to. Okay. So today's lecture is really just kind of looking at implications of that. And there isn't really a proof today even. We're just kind of playing around with those concepts. I mean, I guess we'll call something a proof, but there's really nothing to the proof. Okay? So we're just kind of playing around with that concept from Friday. So, our first definition is just trying to capture which functions are power series. So we're going to give them a special name. But first, let's do the setup. So we've got a function from some domain D into the reals. We are going to insist that that domain D be open. Okay. And then the term we're defining is, we're going to call it real analytic at the point A if and only if it has a power series representation centered at that point So there is that power series. We're going to insist that it converge to f of x. Okay. Now, we can't just insist that it converge to f of x at the point A, because that would allow too much. That would be too lenient. Because power series always converge at their centers. Okay, so what we're going to insist on here is that we converge to f of x in some neighborhood of A. Okay, so we want this to converge to f of x on an open interval centered at A. And we should be careful. The empty set is an open interval, but we don't want that. We want our R to be positive. Okay, now we're going to do our standard thing. It's real analytic on the set D if it's real analytic at all points in D. Okay, and that's our definition. And if it's clear what D is, we'll just say that the function's real analytic. Okay. Any questions about that definition? Oh, Benjamin asked, does D have to be connected? No. No, D definitely doesn't have to be connected. Any other questions? So this definition has some, several parts, but it's really just trying to capture that the function is a power series. The function is represented by a power series. Now, importantly, one thing we did not say in this definition is that it has to have the same power series at every point. It does not have to have the same power series at every point. It just has to have a power series. Okay, now let me show you an example that illustrates that. Look at the function consider f of x equal 1 over 1 minus x. Okay, this is its largest possible domain would be the real numbers minus 1. And it maps into the reals. Okay? Now, is that function real analytic at the point 1?
Well, no, because one's not in the domain.
Oh. I'm sorry, that's not what I meant to ask. Is it real analytic at the point 0?
Yes.
Uh-huh, and what is the power series there?
So the A n's are going to be, the first one is going to, the 0 order is going to be 1, and then all the others are 0.
No. So you're trying to say that f of x equals 1.
Oh, but I need a neighborhood. That's right.
You need a neighborhood. So does this function remind anyone of anything that we've seen recently?
It's the geometric series sum.
Uh-huh.
So it'd be just x to the n.
Yeah.
As long as x doesn't get to 1 or negative 1.
Uh-huh. So we could write that this way. F of x is that power series for all x in the open interval from -1 to 1. Okay. So again, this equality here is a geometric series thing that we looked at in our first day on series. Okay. This shows us that yes, it is real analytic at 0, because we've got a series that converges to f of x on some open interval centered at 0. Okay. Now,
Question about the definition, does that have to be like uniform converging from that variable?
So remember, when a power series converges, if you're inside its radius of convergence, you have uniform convergence.
Right, okay.
Yeah, so we don't have to insist here that it be uniform convergence. We do get that. So we will have, this will always be, this convergence right there will always be uniform. If we're really real analytic. Okay. What about if I asked you a different point? What if I asked you, is it real analytic at x equal 3? So does it have a power series representation at x equal 3?
We could try manipulating our given power series, like by dividing or multiplying by 3, something like that, to give us our desired output of 1 over 1 minus x.
So this is our function. Okay. And even when you know the trick, this is a little bit tedious. And you may or may not have seen the trick in Calc 2. I don't know. Or you might have seen the trick and forgotten it. We want to expand this thing as a series, but centered at 3. Not centered at 0. So we want x minus 3s, x minus 3 to the n in our series. So we're going to manipulate it to get x minus 3s. What I'm going to do is I'm going to subtract a 3 and then add a 3. Okay, so just check that in that denominator, this minus 3 and that minus 3 actually do cancel. Okay. Now, we pull out this part. Okay, how do we pull it out? Well, we divide by it. Yeah, divide by it. We just factor it out. And then what will we be left with? We factored out a 1 minus 3. So that's a 1 minus, and then we have an x minus 3 over 1 minus 3. And yes, I could simplify 1 minus 3 to minus 2, but I'm trying to show you in a way that maybe will convince you this works at other points too. Now, this is 1 over 1 minus 3 times the sum, because this thing has a power series of x minus 3 over 1 minus 3 all to the n. Okay, if we want to put this in a nice form now, I finally will simplify.
Do we have to make sure that x minus 3 over 1 minus 3 is between 1 and -1?
Mhm. Yeah, there's two ways to do this. One way is now just do the root test. You'll do the root test with this thing because of this 1/2 there. Your root test will come back and tell you that your radius of convergence is 2. Okay. Or, if you think about the theorem where we did the root test, that lim sup will be 1/2, and then you divide by 1/2, you get 2. The other way is you can say right here, this step, this is valid for absolute value x minus 3 over 1 minus 3 less than 1. So that would be that interval. Any questions there?
So doing this trick, we've gotten a bigger interval than sort of our, because here we're going from 1 to 5, which goes 4, versus 1 to -1, which is only 3.
Well, it's not 3. It's 2. But yeah, okay. So it's larger. Yeah, I guess it's larger. It doesn't contain the other one, right? This isn't like, so it's a larger interval, but you wouldn't say it's a better interval. It's just a different interval that happens to be longer. Does that make sense?
Yeah, I just thought it was interesting that this trick made the interval larger.
Yeah, so actually the farther you go out, if you try x equal 100, you'll get a larger integral convergence as well. It's not, see, we can't really say much more kind of when we're stuck on the real line. So I guess now would be a good time for me to say, if you've taken complex analysis, you'll know this, or if you're going to take complex analysis, you'll learn this. Functions are called complex analytic, or just analytic, if they can be represented as a power series in the complex plane. Okay, that sounds really similar. I mean, it is really similar, but the two concepts are not the same. Okay, there are examples. So actually, what's going on, if you know some complex analysis, what's really going on is that, this function blows up at 1. And so, anywhere to the right of 1, you're going to be able to get a power series. And your radius of convergence, or let me just say your interval of convergence, it definitely can't include the point 1. Because the function blows up at 1, and power series aren't allowed to blow up. Okay, I mean, that's by their very definition, they have to converge. So your interval of convergence can never include 1. So basically, if you're out to the right, you're centering your power series at the point 100, your radius of convergence is going to be 100. It's going to be 99. Because it's going to be that large. It's going to be as large so that as it can be without including the point 1 in the interval of convergence. Okay. So anyway, this was the point that, yeah, these intervals of convergence do get larger as we go farther to the right. Okay. Now, in the definition of real analytic, let me just say, you know, I said the first time, we don't insist that the power series be the same for all the points. In fact, I could have said something a lot stronger, and I want to go back and kind of fix that. Oops. I said we don't insist it be the same power series at all the points. Well, it literally cannot be the same power series at 2 different points. It has to be a different power series at different points because we're insisting that it be centered at the point A. So when we consider 2 different points, we're going to have 2 different centers. Okay, so in the definition of real analytic, we insist the power series be centered at the point. Yeah, Benjamin, there's a lot. I saw your comment in the chat. There's a lot going on behind the scenes here. I kind of feel like when we're looking at this in a, oops, sorry. There we are. I kind of feel like when we're looking at this in a real analysis course, we only kind of like see the shadows of what's really going on, which is, this is kind of a complex analysis story. Okay, and we sort of see the implications for the real line in this course, but you really see a fuller picture in that course. Okay. Okay, so this trick, where can you do this trick? You could do this trick anywhere except for the point 1. Okay, you can't do this trick at the point 1. So what we end up seeing is that the function f of x equal 1 over 1 minus x is real analytic everywhere but the point 1. Okay. What functions are real analytic? Okay. And so if I don't say, real analytic on a particular set, I kind of mean real analytic on their domain. Okay. Well, how about polynomials? Polynomials are nice. Are they real analytic?
Yes.
Why?
Because they basically are a truncated power series to begin with. So you can just cut off all of the rest of the stuff at the end.
I think you're glossing over
it's
something
just
here.
The one, I keep thinking of just the 1 point.
Yeah. So let's look at x squared. Is the function x squared real analytic everywhere? Well, we have to do some work, right? If we want to center this at A, we're gonna need to make that x squared into an x minus a squared. And then we're gonna be a little bit off because that's gonna be x squared minus 2ax plus a squared. So now we're going to need to add in a 2ax and then subtract off an a squared. Well, now I gotta fix that x term. So we'll need to make that 2a x minus a. And then let's see, that'll actually be 2ax minus 2a squared. So we will need to add in 2a squared. So there you go. That is a power series expansion of the function x squared at the point A for any point A on the real line. Okay, you can check that, yeah, we're definitely, if I did the arithmetic correct, we're definitely converging to x squared in a neighborhood of the point A. And the reason we're doing that is because you expand this thing out, you literally get x squared. I hope, if I did it right. Okay. So in general, how would you prove that polynomials are real analytic?
Induction?
Yeah, induction works. Any other thoughts?
If you had some scheme of producing a power series for an arbitrary polynomial at an arbitrary point, some sort of constructive thing, I think that would be pretty simple too. Well, not simple necessarily, but that would do the trick. I'm thinking of like Taylor series.
Uh-huh. Yeah, so Taylor series is a good answer, right? Why don't you just take the Taylor polynomial of your polynomial at whatever point you want to center it at, okay? And you can check that the Taylor polynomial is guaranteed to be equal to your polynomial, okay? Another good answer, everybody's had linear algebra, right? You studied spaces of polynomials, I hope, right? So you got your one basis for them. That's a basis. But, I mean, this is another basis. So you can just use a change of basis. Okay. Lots of bases for the space of polynomials. Okay. What else is real analytic? You can check exponential, sine, cosine, these sorts of things. Okay. Now, is there a nice, sufficient condition for being real analytic? I'll just jump to the punchline. The answer is no. Not that we're going to see. So we're not going to see a nice, sufficient condition. We're going to see a necessary condition. So let's look at the definition of k times differentiable. I feel like we didn't do this definition last semester, although we could have. So let's say we got a function, just because this is going to be a iterative definition, we need to define once differentiable. Okay, once differentiable is just differentiable. Now, for k at least 2, this function is k times differentiable. If only if it is differentiable and its derivative is k minus 1 times differentiable. Okay. Let's do an example. Let's look at the absolute value of x, all cubed. Is this function differentiable?
Not at x equals 0.
Why not?
Well, it's going to be, it depends on which direction you're approaching the point from. I think.
Perhaps it is best to expand this out. And now you can take a derivative of both of those. And on the right, your derivative is 3x squared. On the left, your derivative is minus 3x squared. But those two functions happen to agree at 0. So actually it is differentiable at 0. Okay. Now you can go take a derivative of the derivative. Okay, and we said the derivative on the right, it's 3x squared, so its derivative is 6x. On the left, it's minus 3x squared, so its derivative is minus 6x. Okay, minus 6x for negative x, 6x for positive x. We get f double prime is 6 absolute value x. okay? That, so its derivative is still differentiable at 0. So f is twice differentiable at 0. Oh, but then we cannot take a derivative of this at 0. Okay, you take a derivative of this, you'll get its derivative is 6 for positive x and minus 6 for negative x. So f is not thrice differentiable. And you can extend this pattern if you want. Look at the absolute value of x raised to, right, so absolute value x raised to the k plus 1 is k times differentiable. And it's not k plus 1 times differentiable. Okay. Now, a lot of our functions that we like, polynomials, exponentials, sine, cosine, these things are differentiable as many times as we like. I mean, in the polynomial case, you eventually get 0, but that's fine. You just can keep taking derivatives as 0. So these functions are infinitely differentiable. Let's just define that. Okay. It's infinitely differentiable if it's k differentiable for all k. Or another word you hear a lot is smooth. Okay. So if you hear that a function is smooth, that means that it's infinitely differentiable on its entire domain. Okay. Here's a proposition. The short version is that real analytic functions are smooth. So we need to qualify this a little bit. If the function with domain D, where D is an open subset of R, is real analytic on its domain, then it's infinitely differentiable there too. On D. Okay, any questions about the statement here? I said at the beginning we wouldn't have a proof, and then I said, well, we kind of will have a proof, but it won't really be much. This is it. There's really not much to it. Let's suppose that F is real analytic on D. Let's take an arbitrary point, and we will expand F as a power series there. Okay, so since F is really analytic, it's equal to a power series centered at A, for all x in some interval, also centered at A, for some r greater than 0. I didn't write this the first time, but I probably should also write this. Right. There is a sequence A sub n of coefficients such that f of x is equal to this power series for all x in this interval centered at A. Okay, well, and what we said is that from the last lecture, where your power series converges, you're differentiable. Okay, and not only are you differentiable, but you get your derivative by term differentiation. So your derivative is also a power series, okay? And we showed that it has the same radius of convergence. So you can just keep iterating this result from the last lecture, and we can take as many derivatives as we want. Okay. So by iterating our result from the last lecture, we can take as many derivatives as we want. So, like I said, there's nothing to this proof. I just want to stress the one issue that you want to be a little bit careful about. Again, going back to the beginning of lecture, if you're real analytic, you get a power series, but it has to be centered at that point. Okay, so you have to argue about a specific point, and you have to center your power series there. Okay. In fact, we get quite a bit more from what we did last lecture. We can actually just compute this. Okay, so now we've only got a couple minutes left, so suppose that f of x is the sum an x minus a to the n. Then we can write its derivative Benjamin asks if we need A minus R, A plus R to be in D. I think I said that when I said it was real analytic. Yeah, we insist that it be real analytic there. I mean, we could, yeah, sure. We can add some in D. Okay, so we can compute these derivatives. Let's see. Right, the derivative of one of the, the first derivative would be n a n x minus a to the n minus 1. But then you'd probably re-index, so you'd actually get n plus 1 a n plus 1 x minus a to the n. Okay. And now you take another derivative, the n comes down, you re-index. Okay. So what you'll end up with is I don't have enough room here. N plus 1, n plus 2, etc. I'm going to go the wrong way, kind of. Okay, its kth derivative is that power series. You can go through the root test, has the same radius of convergence. We have a theorem that says it would anyway. We can simplify this. I like this form better. Kind of up to you, but this is really n plus k factorial over n factorial x minus a to the n. Okay. Now, from this, we see that actually you plug in A, and you can read off your coefficients. Okay, so we actually can compute that A sub n is the nth derivative of f at the point A divided by n factorial. And of course, this is Taylor's formula. Light again. Anyway, it's almost the end of the lecture. I want to leave you with one more thing. Not all smooth functions are real analytic. Okay. There's a couple classic examples. You can check Wikipedia. Here's my favorite. At the point 0, you can check, it's not the easiest calculus exercise in the world, but it's not that hard, that this thing is smooth. Okay, so again, that means that it has derivatives of all orders at the point 0. Okay. This function, by the way, if you plot it, if you plot it, it's very flat. And then it kind of does that thing, and it's symmetric, so. Okay, here's the point x equals 0. Here's your problem. All your derivatives at 0. are 0 because it is that flat. Okay. So you go and you form the power series centered at 0. By Taylor's formula, it literally has to be the all 0 series. Okay? But this function is not equal to 0 in a neighborhood of 0. It's just very close to 0 in a neighborhood of 0. Okay, so it is not real analytic at 0, even though it is infinitely differentiable. Okay, so let me stop there. I will see you at office hours today or tomorrow maybe, or